Okay, this is a little more complicated derivation. We have two situations. We're not landing on the same plane. That's going to cause us problems because our S will no longer be 0. So that's going to make for some bad math. But this first one up here is called an elevated target, where the target is up above where the launcher is, and that's going to be a plus S. Anything we measure up is going to be a plus S. This next one here is called an elevated launcher. The launcher is above the target, and we're going to have a minus S because we're going to be shooting down below the plane. The same things still apply. We have a velocity which we can resolve into a Vx and a Vy, a horizontal and vertical velocity, as we get with our equations right here. And we're still going to be using our initial range equation, our initial vertical displacement equation. If you remember, range was Vx times t, and if we solve that for t, we'd have t equals range over, and I'll go ahead and put in the Vx equation, v cosine of theta. Our other equation is vertical displacement, which is S equals Vy t plus 1/2 a, or g, in this case t squared. That's our vertical displacement. And what we're going to do is we're going to plug in our time into this equation here. We're going to plug that into this equation here for the time. And we'll go ahead and put in our v sine of theta in for our Vy also when we start this derivation. So here we go. So we're going to start with S equals, and we're going to have Vy in there, which is v sine of theta. And then we're going to, and for time, we're going to put this equation here. So we're going to have range over v cosine theta. Okay, and then we're going to have plus 1/2 g, I'll put g over 2, times t squared, so that's this squared, so it'll be r squared over v squared, and a cosine squared of theta. So it's kind of gets ugly kind of fast. Now in this equation here, if we look at this down here in the end, well, there's a couple things. There's a couple trig identities we're going to put in here. We have right here we have a sine over a cosine, so that's something we can put in. Right here you could technically say we have a 1 over a cosine squared theta. That's another trig identity we're going to put in, solve for. And you'll notice right here the v's will cancel out, so that's pretty nice. So what we're going to have is we're going to have S equals, and we're going to have R. We'll put the R out front to make it look nicer. And sine over cosine is tangent. If you don't know all these, that's fine. You can look those up, and my board just moved. Sorry about that. So R equals tangent theta. And then plus, we're going to have g r squared over 2v squared times, the trig identity we can put in for 1 over cosine squared is tangent squared theta plus 1. Okay, so we're going to put that in there. And so what we're going to do in this next step is we're going to distribute this big ugly gr squared over 2v squared. So it's going to be kind of gross. So we're going to have S equals r tangent of theta plus gr squared over 2v squared tangent squared theta plus gr squared over 2v squared. And what we can do is we can go ahead and we can bring the s over to the right side. So let's just make it a minus s here, and this then will be a 0. So we have everything on that same side. Okay, so what I'm going to do, I'm going to rearrange. I have 4 terms over here on the right side, And I'm going to rearrange them in a little bit different order. I'm going to put the tangent squared term first, and then the tangent term, and then the rest of the stuff later. But what I want to do here is kind of weird, and you just have to kind of bear with me here. It's actually, there's a reason for it, my madness. But I'm going to take this whole equation, and I'm going to multiply it by 2v squared over gr squared. Let me write that down somewhere over here. So let's see, where can I do that? Yeah, I'll just do it here. I'm gonna multiply this whole equation right here, this whole thing, by 2v squared over gr squared. Let's see if I can do this without running out of room. Okay, so here we go. The whole thing. So on the left side, 0 times that big ugly thing is still 0. So I'll have 0 equals, and if I and then what I'm going to do is I'm going to go to the tangent squared thing. So if I take 2v squared over gr squared times what's in front of tangent squared, that's nice because that cancels out perfectly, and it's tangent squared theta. Okay, and now I'm going to do the tangent theta. So what would that one be? That'll be plus, let's see, that'll be 2v squared, 2v squared over gr, just one r, because one of the r's canceled out there, tangent theta. Okay, plus, this is going to be 1, right? Minus, and then I'll have 2sv squared over gr squared. Okay, that equation is actually really ugly, but it's about as simplified as we can get. That's a nice and important equation. And what I want you to notice here is that this is the same equation as 0, not theta, 0 equals ax squared plus bx plus c. That's a quadratic formula. That is in a quadratic formula equation. But what is x? There's no x up here in this thing. What is x? Well, x is tangent theta. So you'll see here x squared, there's tangent theta squared. Here's x, there's tangent theta. Here's c, there's a big ugly c term right there. So what we can do is to figure out the angle, we're going to be using this to figure out the two possible angles that we need to shoot to go a certain range, a certain vertical displacement, and so on. And what we can do is we can figure out, we can get our A, our B, and our C value and put it into a quadratic, the quadratic formula in our calculators and get two answers. And from those answers, we can figure out our angles. So what is A? So all we have to know, we don't really have to memorize this big ugly equation. We just have to memorize what A, B, and C are. A is 1, so that's really easy. B is what? What's in front of the tangent theta? B is 2v squared over gr. So we'd have to take 2 times the velocity squared divided by negative 9.81 divided by the range, and we'd have our B value. C is the ugliest one of all. It is 1 minus 2sv squared over gr squared. So we'd have to put all that in. Because we're in our program that we're going to be writing, we're going to enter in a vertical displacement, a velocity, a gravity, and we're going to enter in a range. So that's all we need. The user can enter those in. We can figure out an A, a B, and a C, stick it in the quadratic formula, get our two values, and figure out the two possible angles. Now, when we get the two values from the quadratic formula, are those going to be the angles? No, they're not going to be the angles. Those two values are going to be what? They're going to be x, which is, in this case, tangent of theta. So when you get your two values from your quadratic formula, don't just assume those are the angles. You have to actually take the inverse tangent of those answers, and then you'll have your two possible trajectory angles. Now, the thing to remember on this one is this different than shooting and landing on the same plane. I mean, that's the whole reason we have such a complicated equation here, is because we can't put in 0 for our s. See, we had to leave s in this equation. We couldn't put a 0 in for s. And therefore, we couldn't divide by a time and get rid of the squared, so we have a quadratic. It's always going to be ugly when you're not shooting and landing on the same plane. The other thing to remember about this is that these angles that you come up with, these two angles that you calculate from the quadratic formula, are not going to be complementary. So there's a temptation for my students to, once you get the first angle, to subtract it from 90 like you did when it shot and landed on the same plane. That is not the case here. You can't subtract it from 90. You need to take both values, take the inverse tangent of both of those values to get both of your angles for elevated launchers or elevated targets.